So think uh, your computer as a restaurant. So if you ask you a question, let's say you're in a restaurant and you've placed an order. Now, who makes sure that your orders are uh, cooked and served on time? Now, who makes sure of this? So I think the most reasonable answer is the head chef. The head chef will receive the order, and he will put things in process, or he will have some assistants to help with. And when once the dish is cooked and it has to be given out, okay, and you will receive the dish. So probably this is the process. And in this world of computer science, the head chef is the operating system. The operating system also manages multiple things. It takes a request from the user and it does some computations and it gives you an output. So to cook a proper dish, there are some prerequisites, right? Few are first of all, the order must be it has to make sense. Just like that, you can't walk into a restaurant and ask for an eggless omelette, right? So the order has to make sense, and there has to be a recipe, and we should have ingredients, most importantly. So in computer science, if the OS has to do some work, I'm putting things in a crude way. So there has to be data, proper data, and instructions, right? So instructions or otherwise called as programs. So much like a recipe, a program is also a step-by-step instruction and hardware. So basically, this is what an OS does. Uh, uh, I sort of give you a definition. OS connects users with computer hardware. Now, why? So you're the user, mm, and if you want to communicate with the hardware, it's not that easy. It's really difficult because the hardware consists of microprocessors. There will be cables running from one end to another, and there are integrated circuits. And everybody can't do this binary sort of thinking. So this is a smart solution. So on top of hardware, there's a software which is called as OS, which takes a request from the user and gives back an appropriate response. And the response, if there is no response, probably it gives an error message with sort of another response. So all the computations will be done in here, the hardware, and the OS will sort of facilitate it. So that's the idea of having the OS. Now, I'm sure you've all used an OS before. Maybe it could have been Windows or Linux, or Android or OS. There are multiple OS in the market. But did you know that all OS are not built the same? So some run in mobile phones, others control missiles, and some just sit quietly uh, on servers, process data all night. So each of these systems need unique things. Okay, so that's why OS comes in different types. So every OS is optimized for a particular kind of job. Uh, so so if I sort of ask another question like what's a good OS? Okay, I mean this is a natural question, right? So if there are multiple OSs, I want the best one. Then how to define a best one? Should it be super fast? Should it never crash? Or should it be damn easy to use? Does it have to work on every device? So how should it be? But the truth is, different OS are built to do different things. So there is no one size fits all OS. It depends on the use case. Let's say if it's going to be a pacemaker, there the decisions has to be very quick and it shouldn't fail. Uh, So there will be a type of there we will use a type of OS where uh, reliability takes precedence over convenience. But in your mobile phones, convenience is much better than reliability. So there are different OS to do different things. But what are these types of OS, right? So types of OS. Now, to understand types of OS, let's start with the structure of memory. Okay, so let's assume this is memory and there are a lot of pigeonholes. Okay, there are a lot of pigeonholes, and each pigeonhole will have some data. Okay, and 6521555. So there's some random data. These numbers are data. We have data, and we also have six, two, two. We also have instructions. This is memory. So memory contains of data and instructions as collectively called as a program. So these instructions will say what to do with the data we have. So these instructions are not linear, first of all. It can jump from here to here, and it can sort of loop again. So the instructions will say, okay, I have this much of data, and probably I'm going to calculate A with B or something. And a CPU will take care of all these computations. Now, now let's say this memory, I'm going to assume it as a magnetic tape, okay, which is going to be spinning, and there's a bunch of users, okay. They all have some computations to be done. So what they're going to do is they're going to give their programs into this magnetic tape in a batch. Okay, let's say this is batch number one, and this is CPU. There's sort of a limited or primitive kind of CPU. It calculates one problem at a time, and the output is recorded in another magnetic disk. So this is the input, and this is the output. And this output is collected by, again, the users. You have given the input and waiting for it. Now, this is what we call as batch processing. So all the inputs are divided into different batches, and those batches are given as input to the CPU, and we'll get an output. So there are many limitations on this kind of batch, on this type of batch processing, where uh, you'll get an output after a long time. So whatever response you're getting from the CPU, it's not immediate. It can take few hours to weeks, depends on the calculations in the batch. And once the batch processing has started, there's a chance that errors can go unnoticed. So what I mean is if there's an error, let's say in the first batch, there's an error somewhere in the middle. but you might not even realize it until the whole thing is done. So nowadays we have very interactive systems. Let's say you're doing some program. You once the moment you click run, the program runs, and if there's an error, you'll get an message that so and so is error, and we can't proceed anymore. But in earlier, the batch systems are not like this. The entire batch has to get finished. Only then you can understand, okay, the error has been made. So we'll improvise. We'll improvise now. Okay. Again, let's have this batch system here. Magnetic tapes, the same CPU, another magnetic tape. What I'm going to do is I'm going to attach some consoles. And user 1, user 2, user 3, user 4, user n. Okay. So there are multiple consoles attached, and every console is used by a user. Uh, so now what happens is these users are sort of slicing the CPU for themselves. What I mean is everybody is going to calculate. Or, or let me put it in this way. The CPU is going to calculate programs in short burst. Let's say user one's program should run for 10 seconds. User two's program will run for 2 seconds. So, and there's a now I'm fixing a timer, okay? A timer to let's say 2 seconds. Initially, the CPU will be here. It calculate user one's program for 2 seconds, okay, and then it moves to user two, okay. This is called short burst. So now the 10 seconds will be reduced to 8 seconds. Later on, the 2 seconds will be over. So this work is done. Again, it goes back to user one. Again, it calculates for works on for 2 seconds. Now it becomes six. So it goes on. This is called working for short burst. Let's rearrange the whole memory thing with this new interactive system. Let's say now we have memory again. In memory, I'm going to dedicate some space. It's called a supervisor. This is the master program. And initially we have pigeonholes. Now we are going to dedicate some space for users. Let's say user one, user two, user three, user four, and have this big magnetic disk. This is a very large space. Mhm. So what will this do is the all these consoles they will communicate with the supervisor, and the supervisor communicates with the magnetic disk, and let's say there's a pool of programs first of all in this magnetic disk, and the supervisor will load the programs into the main memory. So this is the main memory we have. So the way it loads the program into the main memory, it has some certain algorithms. It follows some structure. Okay, so that loading is called as CPU scheduling. CPU scheduling is can be defined as which program. gets to utilize CPU for how long. Okay. So that is done by the supervisor. So initially, uh, there will be a timer. Okay. Okay. So after a certain point of time, let's say 2 seconds, the control will go back to the supervisor. Okay, let's say the control is here right now. It's here in use of 4. After 2 seconds, the control again will go to supervisor. Okay, and now the supervisor decides which program should be loaded into the memory. And I'm saying it's user 3. So now the control will be here. Again, after 2 seconds, the control will come back. It goes to user 2, controls come back, and user 1. So like this, every user will get short amounts of time, a window to utilize the CPU. This is called as time sharing. This is a type of system which is an improvisation over the batch processing. It's called time sharing. Now let's look at the definitions. Batch processing, when the computer runs a group of jobs, one after another, without user interaction. And we've looked, there are certain limitations to that. In time sharing, when computer quickly switches between user or programs, uh, in time sharing system, the supervisor will help to switch, giving each or small size of CPU time, which is called as burst. So it feels like they are running at the same time. So it sort of simulates a degree of multi-programming. And we also have other OS like real-time OS, and I will give that up to you to explore. But these are the predominant types of OS. Now that we have seen different types of OS and we have understood that each OS is built for specific tasks like batch systems or time sharing, what exactly is inside an operating system that makes all this possible? We've in this program in time sharing we looked there's a program called supervisor. It speaks to the magnetic disk. There's a program called supervisor. It speaks to the magnetic disk, and there is some sort of scheduling algorithm that is going on, which loads the memory, which loads the program into the memory. So, what exactly is making an operating system to do all this? So, no matter the type the OS is, every OS has some common components. So, these components work together to manage processes, memories, devices, and users. So let's explore these types of or OS components, let's say OS components. So what are these components? First is a kernel, there's a shell, file system, device drivers, system calls. So now the idea is to try and understand these concepts by looking at a sort of evolution of OS. Okay, let's start with cru- a diagram. It's sort of crude diagram. Okay, so this is. the hardware and drivers. This is the OS, and there's an app. Okay. So let's say app is running. It's called a browser. Let's assume this is a browser, and the browser wants to uh, uh, get some information from the hardware. Let's say from your hard drive or something. It needs to talk to your underlying hardware. So it interfaces or talks with the drivers, and this drivers enables a sort of communication channel with the hardware. So in essence, device drivers are special programs that help the OS talk to hardware. Now look at this. Here I have mentioned app. It's not apps, it's just a single app. So this is a system where only one application can run at any time. It is also called as uniprogramming. Now, in the upcoming years, tech got smart. There were a lot of uh, advancements that were going on in the field of OS, and the OS itself became very large and very complex. It was built piece by piece. Since it is built piece by piece, each part of OS has its own inputs, outputs, and functions. So what I'm going to do is I'm just going to restructure the diagram and I'm going to add the new updates. Okay, let's say now this is the hardware, and on top of it we have this large and complex OS. Again, it was built piece by piece. On top of it, we have multiple apps. App 1, App 2, and App N. Okay, there are multiple apps. Now the OS sorts of opens an interface. All those apps are communicating with the OS and OS is communicating with the hardware. So the right term is an interface opens an interface. Now this interface, it doesn't have to be between OS and hardware alone. Okay, there are multiple kinds of interface. First of all, the user can talk with the OS, and the app can talk to the OS. So, what's the difference between user and app? User is you are trying to run a program that is called user and OS. Let's say you ran a program, and that program is dependent on some other program. So, that some other program is going to be called automatically. That is between the app and the OS. And we have OS and hardware. So this part we've already looked at, and this interface is called as device drivers. Now we'll look at user and OS, okay? And to sort of give a definition for interface, it's a communication layer between two parts of the system, right?